Hi there, glad you could join me. I'd like to talk to you about a couple things involving circles today. And those things that we're going to discuss are called inscribed angles and then inscribed polygons. Two goals here. One is that you're going to be able to find the measures of angles that are inscribed in a circle. And so I'll have to tell you what it means for an angle to be inscribed. And then we'll see the relationship between the measure of an inscribed angle and the measure of its intercepted arc. And also you're going to learn to inscribe right triangles and to inscribe quadrilaterals in a circle. There's some certain conditions that have to be met for those things to be done. I'll explain to you what they are and help you see a couple ways in which those will be used. So let's discuss inscribed angles. First, what does it mean for an angle to be inscribed? Well, I've got an angle that's inscribed here, this angle ABC that you see. And what makes it inscribed is that it's formed by two chords whose intersection is a point on a circle. And anytime you have two chords or two secants whose intersection is a point on the circle, then you have what's called an inscribed angle. And there's a very specific relationship between the measure of an inscribed angle and the measure of its intercepted arc. And so what I'd like to do is kind of demonstrate to you why, this is more or less a proof, to be honest, demonstrate to you more or less what that relationship is and why it is that way. Now let's start by discussing the arc that's intercepted by this inscribed angle measure. All right, you're going to see that this arc here, AC, is what they call the intercepted arc of our angle. Now, what we're going to do is we're going to use that arc measure in order to find out what this inscribed angle measure is. And you might recall that the way that you find the measure of an arc is by the measure of a central angle that intercepts that arc. And so I'm going to add a little bit to this picture here. I'm going to go ahead and add another radius of a circle that is going to create a central angle that would intercept this arc also. And so let's say that this, if I connect points A and Q, is going to form that central angle that I was referring to. Okay. Now, one thing I should note also is that in this example, one of the sides of the inscribed angle is the diameter of the circle. It went through the center of the circle, right? All right, that'll be more relevant later. Well, so how then could I find out what the measure of this intercepted arc is? Well, notice that this triangle ABQ that I made, since two of its sides are radii, have to be congruent to one another. This is an isosceles triangle, right? And so if this angle ABC is x degrees, that would mean that this angle BAQ is also x degrees. All right, now it's been a while since you've used this probably, but this angle AQC, the central angle, whose measure I'm going to use to find this arc measure, happens to be an exterior angle for that triangle ABQ. And what you might recall is that the measure of an exterior angle of a triangle equals the sum of the two non-adjacent interior angles. So in other words, if I add that x and x together, it's going to give me 2x degrees. And because 2x degrees is the measure of the central angle AQC, that means 2x degrees is also the measure of that intercepted arc AC. And what I really want you to notice then is the relationship between that arc measure and the inscribed angle that intercepts it. It's twice as much, isn't it? So, another way of saying it is that the measure of an inscribed angle, or this inscribed angle, was half the measure of its intercepted arc. I'll write that out in equation form. There you go. Now remember I showed you, I made the point that one side of this angle, inscribed angle, was a diameter. Well, what happens if you have an inscribed angle and neither of its sides go through the center of the circle? Or in other words, you have one of these two pictures right here. Is the measure of the inscribed angle still going to be half the measure of its intercepted arc? Well, I've got the only other two possibilities that you can have. If the center of the circle is not on one of the sides of the inscribed angle, then it could be between the two sides or in the interior of the inscribed angle, or it could be in the exterior of the inscribed angle. Okay? Now, what I'm going to do is I'm going to show you what the relationship is between the inscribed angle and the intercepted arc for when the center of the circle is on the interior of the inscribed angle. And then we'll just kind of generalize. I'm not going to go through this same process for the second circle, but whatever I find here is going to apply there as well. Okay, what I'm going to do is I'm going to add a picture here, or add a little line actually. And what I'm actually going to do then, for that line, is I'm going to draw a diameter from the vertex of our inscribed angle. And then what's going to happen is I'm going to go ahead and label the two parts of angle ABC as x degrees and y degrees. And I'm basically going to do what I did with the previous example, but I'm going to do it twice. And what I mean by that is I'm going to make two different isosceles triangles. And I'll explain what the point of the isosceles triangles is again. The arc that's intercepted by our inscribed angle, whose measure we're trying to find, is arc AC, right there. And so again, what I'm trying to do is find out what would its central angle measure be, and this angle AQC would be that central angle. And now that I've made the two isosceles triangles, because, well, whoops, that's not what I meant to do. This distance and this distance are congruent. Alright, so that triangle is isosceles, and that's x degrees. And also, this distance and this distance are congruent. They're both radii of the circle. And so, triangle AQC is also going to be isosceles, so that's y degrees. And then if I do that whole exterior angle of a triangle theorem that we were talking about a moment ago, that would make this angle 2x degrees and this one 2y degrees. And so the measure of that arc would be 2x plus 2y degrees, which is equal to twice x plus y. So does that mean that the measure of the inscribed angle is once again half as much as the measure of the intercepted arc? Well, yeah, because the measure of the inscribed angle there was x plus y degrees, so indeed it is half. And let's just go ahead and generalize. The measure of an inscribed angle is always half the measure of its intercepted arc. That's a fact you're going to have to know right there. Now, finish up this slide by saying, even though I'm not going to go through that proof for when the center of the circle is on the exterior of the inscribed angle, if you draw this diameter from the vertex of the inscribed angle, then perhaps you will be able to show that indeed this arc measure AC is twice the measure of its intercepted, its inscribed angle again, okay? Great. Well, let's use this fact. Here are a couple problems where we're going to have to use inscribed angle measures. All right, now in this first circle, we're going to try to find the measure of arc BC. The directions we're finding indicated measure, the measure of arc BC. So we're going to try to find this. Whoops, that's not what I meant to do. I meant to just point here. We're going to find the measure of this arc. Let me highlight that. And in order to do that, we're given two pieces of information. The measure of this arc AB is 132 degrees, and the measure of this inscribed angle ABC is 42 degrees. Okay, well, here's what we're going to do. We're going to use the fact that the measure of an inscribed angle is half the measure of its intercepted arc, and using that fact, then we'll find that the measure of arc AC is 84 degrees. And then, notice that arc BC plus arc AC plus arc AB make up the entire circle. So the sum of those three arcs is going to have to be 360 degrees, which means then that we can say that the measure of arc BC would equal 360 degrees minus the sum of 132 degrees and 84 degrees, those other two arcs for the circle. And so that gives us 360 minus 216, which is 144 degrees. All right, pretty simple way to use the inscribed angle measures, right? Let's try this part B. We're going to try to find the measure of angle PRS. Now I'm going to highlight that as well. This is angle PRS right here, and it's an inscribed angle. All right, now if we're going to find the measure of an inscribed angle, we pretty much need to know the measure of its intercepted arc, which I'll highlight in a different color. This arc PS is the arc intercepted by that angle. So how are we going to find the measure of that? Well, the only measurement we're given is the measure of angle PQS, which is an inscribed angle. But notice that angle PQS intercepts the exact same arc as the inscribed angle that we're trying to find. Okay? So we could do this. We could double the measure of angle PQS in order to find that arc measure. Twice 168 is going to be 136 degrees. And then the measure of angle PRS is going to have to be half of that, so it's going to be 68 degrees. Now I'd like us to make a generalization there. You notice that we had two inscribed angles that both intercepted the same arc, and anytime you have multiple inscribed angles who intercept the same arc, those inscribed angle measures are always going to be equal to one another, just as those were each 68 degrees right there, which is pretty cool. Alright, so let's move on from inscribed angles. And let's move on to talking about inscribing polygons. And there were two types of polygons that I said I was going to discuss with you in terms of how you might inscribe polygons in a circle. And one of those was right triangles. Well, it turns out it's incredibly easy to inscribe a right triangle in a circle. And if we use what we learned about inscribed angles to do that, then this makes complete sense, okay? Now, remember that the measure of an inscribed angle is half the measure of its intercepted arc. And so if we want to create a triangle that has a 90-degree angle, what we can do is create one so that it's made up of an inscribed angle that intercepts a semicircle. You agree that that arc AB that I just highlighted is 180 degrees, right? So, if I make an inscribed angle from the two endpoints of this diameter, let's say we connect A or B to that point on the circle, and then A, and then back. Well, this, let's call that point C right there. Angle C has to be half of 180 degrees. That's the arc that it intercepts, and so that guarantees it's going to be a right angle. And I don't care where we drew this point C, as long as we made the endpoints of a diameter. Hold up, trying to draw it. As long as we keep two sides of the triangle as the endpoints of that diameter A and B, then that third angle C is always going to intercept a semicircle, and thus it's always going to be a right triangle. So, the following fact is true. If a triangle is inscribed in a circle, and one of its sides is a diameter, then it is a right triangle. Always going to be the case, which is pretty cool. Now let's also talk about quadrilaterals that are inscribed in a circle as well. Whereas I could have inscribed any kind of triangle I wanted in a circle, whether it was acute or obtuse or right, because all I had to do was make 3 points on the circle and connect them. I can't just inscribe any kind of quadrilateral in a circle. All right, I can't just say that parallelograms and trapezoids and squares and rhombuses can all be there. There's a very specific thing that's true about quadrilaterals that are inscribed in a circle. Now, I've just inscribed a quadrilateral. It happens to resemble a kite more than anything else, but it's not like only kites can be inscribed in a circle. What is true, though, is what I'm about to describe to you. What I'd like to do is I'd like to look at the relationship between the opposite angles in a quadrilateral that is inscribed in a circle. And I'd like to call your attention to angle A first, and then its opposite angle C. Now let's look at the sides of angle A, which are here and there. And what I'm trying to do really is just point out which arc intercepts or is intercepted by angle A, and that would be this arc right here then, wouldn't it? And then let's look at the two sides of the angle opposite from A, which is C, right? So here are its sides, and here then is the arc intercepted by angle C. Now, do you notice that those two arcs take up the entire circle? So even though we don't know exactly what the measure of angle A is, and we don't know exactly what the measure of angle C is, we know that the arcs that they intercept form the entire circle, which means that the sum of angles A and C is going to be half of that. those are inscribed angles, right? So it turns out that this is true. The measure of angle A plus the measure of angle C equals 180 degrees. All right, then let's compare angles B and D. Here are the sides of angle B, and you see that it intercepts this arc here. And here are the sides of angle D, and it intercepts the rest of the circle, doesn't it? Okay, so angle B and angle D also have to add up to 180 degrees. All right, and then to summarize what I'm trying to teach you there, the only way you can inscribe a quadrilateral in a circle is to make it such that both pairs of opposite angles are supplementary. And conversely, anytime you inscribe a quadrilateral in a circle, its opposite angles will be supplementary to one another. All right, really cool. Now let me show you how you use both of those facts that I just showed you about right triangles and quadrilaterals in terms of problem solving, and then we'll be done here. You see the directions for this problem are to find the value of the variable or variables if there are more than one, but in this picture there's only one. And you see that x is the measure of angle A, and that angle A is an inscribed angle, but more importantly, I hope you notice that it's part of this inscribed triangle, and a little bit further than that, that inscribed triangle, one of its sides is a diameter, right? And we said that any triangle inscribed in a circle where one of the sides of the diameter is going to be a right triangle, which means that angle B has to be a right angle. And so all we have to do then is use the fact that since it's a right triangle and the acute angles of a right triangle have to be complementary, we can use that to say that x would have to be equal to 90 minus 31, so it would have to be 59 degrees. All right, that was a very simple application of what I taught you about inscribed right triangles. Now let's look at something involving quadrilaterals. All right, this one's going to take a little bit more time to do. Nevertheless, you'll get what I'm doing with it. You see 4 variables we're trying to find the value of: A, B, C, and D. 3 of them angle measures within that inscribed quadrilateral, and then one of them is an arc measure formed by 2 vertices of that quadrilateral. Okay, now I tried to set it up so that we could go alphabetically here. Not that that works with every problem, but that is the way I set this up. And remember the fact that we learned about inscribed angles, about inscribed quadrilaterals, is that their opposite angles have to be supplementary. And so you're going to notice that the angle opposite from angle A right here is 101 degrees. Well, that means A has to be 79 degrees then, because those are supplementary. All right, so now we know that this is 79 degrees right there. How can we use that to continue alphabetically and find B? Well, let's look at the angle that's 79 degrees. These are the 2 sides of it, and this is the arc that it intercepts right here. You're going to notice that B plus 95 is the measure of the arc that's intercepted by that inscribed angle, and it has to be twice as much as that inscribed angle, doesn't it? So B plus 95 has to equal twice 79 degrees. Now, let's not worry about the units so much. So B plus 95 is going to equal 158. And so B is equal to 63. All right, now how about angle C? Well, what I'm going to do for angle C is I'm going to use its intercepted arc. But part of that intercepted arc is going to be this arc RS, so we don't have a measure for. However, you're going to notice that we now know 3 of the 4 arc measures that make up that entire circle. So if we add these 3 arc measures together and we subtract that total from 360, we'll find the measure of arc RS. All right, so I'll go ahead and do that really quickly. That gives me 161 degrees. And then what I'll do is I'll take a look at that arc that I was talking about that's intercepted by the angle that is C degrees, okay? So there's that angle. Here's its intercepted arc. And that arc has to be 161 plus 63 degrees, right? So 224 degrees, which means that C is half of 224 degrees, or 112. All right, so almost done with that. There's 112 degrees. Finally, to find the measure of angle D, well, it's the opposite angle of that inscribed quadrilateral from C degrees, and so they're supplementary. So we can go ahead and say that D is equal to 68. All right, because 68 plus 112 is 180. Now you know how to measure inscribed angles, and you know how to inscribe right triangles as well as quadrilaterals within a circle. Pretty good stuff. Hope you enjoyed it. Hope you learned a lot. See you later.